Welcome back to part 2 of our video lecture on Chapter 8. Now this slide has a lot of red on it because this is an important slide. It's one to add to your cheat sheet when studying for the exam coming up. The routing process. Routers route by using a routing table. That's how they keep up with the information of what the path through the internet is. Routes are simply ranges of IP addresses where packets get forwarded. The routing decision down here, this is the meat down here. Simple three-step process. Every single router works this way. It'll go through its routing table and find all the row matches, not the first one, all row matches. Then it'll determine the best row match based on an algorithm. And third, it'll send the packet out based on the row. I'm not sure why that says send the frame out. That looks wrong to me. You're sending the packet out. It's an IP packet. I think that's just wrong. Anyway, here, let's just change it. Boop. Packet out. Boom. Just like that. So find all row matches, find the best match row, send the packet out. Those 3 steps. So if we dive into the first step of find all rows, there's some more verbiage that tells you what the router's doing. So you might have multiple matching rows at the end of this process. And then the step 2, finding the best match row, the book gives you kind of a common way of doing it. I would put it to you that it depends on the manufacturer, and even more than the manufacturer, the routing protocol you're using. So this is in a future chapter, but routers can use different algorithms for calculating the best path. There's no one best way to calculate the best path. There are different ways of calculating it. So IGRP is a routing protocol that is a very simple one. It's actually part of the TCP/IP stack, hence it's open source. I can't even speak. Open source. EIGRP is a Cisco variant of IGRP that's a lot more sophisticated. I misspoke. RIP, Routing Internet Protocol, is the common one that belongs to every, that's part of the TCP/IP stack and is open source. I'm rambling. This is stuff that we'll get into in a future chapter. I'm just saying the way it finds the best match row is it depends. It's through some kind of metric, and looking at a cost metric or a speed metric of that path is a common way of doing it. Step 3, send the packet back out. And here I said packet, which is correct. Yay. It's at this point that I like to bring up a question that a student asked me years ago that at first threw me off. This was like in my first year of teaching. And I remember him saying, well, for routers, you say routers understand IP addresses and switches understand MAC addresses. Well, when the router hands off the packet to a switch, how does the switch know what to do with it? If switches don't understand MAC addresses and routers don't understand, and if routers don't understand MAC addresses and switches don't understand IP addresses, how does it jump from layer 3 to layer 2? How does it do that? The answer, and at first I was like, oh my god, it's magic. How does this work? And then I remembered, oh yeah, that's why we have ARP, the address resolution protocol, that translates, it resolves an IP address to a MAC address. You can do this yourself if you open up a command prompt right now. Here, I don't care, let's do it right now. You can type in ARP at the command line. If you type in ARP, it should give you, the syntax, but if you just do an ARP -A, it'll show you the IP addresses and MAC addresses that it's got in its ARP table right now. So your router has an ARP table cached that looks just like this. So does your PC, so does every device that's running TCP/IP. You can run ARP on any device that's using TCP/IP. Now that's it for routing. Now I'm going to switch over to the topics around IP addressing. I realize I'm going through this very quickly because in a video lecture it's easy for me to kind of bounce from one idea to the next, and you'll anyway, the burden's on you at this point. With an online lecture, I can't see your faces. I can't see if you're getting it or not, if I'm going too fast or too slow. You've got to reach out to me and let me know how I can help you. If there's a topic that you just don't get around routing or IP addressing, please let me know. Okay, now we get to do a deeper dive into IP addresses, and there's some concepts we need to look at before we can actually start calculating IP addresses. You need to understand that IP addresses fall into a hierarchy. And every single IP address has 3 parts, but it's a little difficult to disentangle the 3 parts. But in general, the network part of an IP address, say, is like the zip code. A subnet would be like a street address, or a city. Let's say a city. A subnet would be a city, and then a host would be like a street address. So the 3 parts of any IP address are the network part, the subnet part, and the hostnet part. Now a firm divides up its network into subnets for the same reason that you don't take all your paperwork and shove it into a filing cabinet without any rhyme or reason, without any folder structure or anything. Creating subnets on your network is usually for organizational logic. You might have different subnets for different departments. You might have different subnets for different locations. It's just a way of keeping the traffic flow somewhat logical and keeping your IP address scheme logical with a business logic to it. There's an example in the book, but keep in mind this is just an example. For example, in the University of Hawaii network, 128.171 is the network part of their address. The subnet part is this 3rd octet, and the host part is the 4th octet. It's just an example. You have no way of knowing which part is which on an IP address just by looking at it, and this is troublesome. Another example, I think this is from the previous edition of the textbook. The far left part will belong to the network. Here it just happens to be 16 bits. It doesn't have to be 16 bits. The subnet part here is 8 bits, but it might not correspond to the 3rd octet necessarily. Same with the host part. The host part will always be the farthest right, but you don't know how many bits there are for the host. You do know, beyond a shadow of a doubt, how many bits total you have for addressing, and that's 32. So what we're doing is chopping up 32 bits into a network part, a subnet part, and a host part. And these are decisions we have to make ahead of time as we're designing the network. Like I said, we have a huge problem. Just by looking at an address like 192.168.1.1, you have no idea which part belongs to the network, which part belongs to a subnet, which part belongs for host addresses to be assigned. You just can't tell. There is a solution, though. The solution has everything to do with Halloween. How appropriate is this? Masks. So the thing that helps us determine what part of an IP address belongs to the network is called a subnet mask. And so that's why I have a Homer Simpson mask up here just as a silly reminder of what we're talking about. Another way of thinking of a mask, this is the way I think of it, but if it doesn't help you, ignore this. It's a way of covering up part of the address. So what I'm doing here is covering up what belongs to the host, and what's revealed, this all belongs to the network portion of the address, like the zip code. So a mask just covers up part, same way a mask covers up most but not all of your face, because you've still got, like little eye holes on a mask. It's a mask. Now here's where you're going to screw up on the exam. I'll tell you where you're going to screw up on the exam, because everybody screws this up on the exam. Don't confuse a subnet mask with a subnet. A subnet is just a logical way of dividing up your network, according to business decisions. You divide your network into subnets by department, by location, by product, by functional area. A subnet mask simply tells you which part of an IP address belongs to the network. That's it. That's what you have to memorize. A subnet mask tells you what part of an IP address belongs to the network. Now, the way I was taught that IP addressing works, at the most fundamental level is that you need exactly 3 pieces of information for IP routing to work. And we're kind of going back to routing for a second here. You need an IP address, you need a subnet mask so that it can tell which part of the IP address belongs to the network, and third, you need a default gateway address. So if you do an IP config at the command prompt, you'll see that you get these 3 pieces of information. That default gateway is your next hop router. It's the interface of your closest router. It's 1 hop away from you. And now for some math. Don't worry, don't panic. This is not computer science. This is easy math. It's not calculus. Remember, we had one formula that we used before to determine the number of mathematical alternatives for addressing. And that was 2 to the n, where n represents the number of bits you have in the address. Remember Bucky and IP addressing, that silly video? So 2 to the n is our formula. The real formula is 2 to the n minus 2. The reason you have to subtract 2 addresses, it doesn't matter if it's 2 to the 256th power, you still have to subtract 2 addresses because we reserve the first address and the last address. The first address is the nowhere, sorry, not the nowhere address, that's the bit bucket. The first address is the ID of that network. The last address is the broadcast address, okay? So if you send a packet to the broadcast address, it's going to send it to every single node on that subnet. So how might we subnet a network? How do we decide how many bits to use for the network? Well, one option would be just to divide them in half. We'll use 16 bits for the network and 16 bits for subnets and hosts, and see what that gets us. Well, out of 32 possible bits, if 16 I can't change because that belongs to the entire network, and I've got 16 bits to play with, maybe I'd split those in half, 8 and 8, to have 8 bits for the subnet and 8 bits for the number of hosts per subnet. So I'd have 2 to the n minus 2 possible subnets for 254, and the same number of possible hosts per subnet. Now, is that right for my business? I don't know. Am I going to have 254? Do I need 254 different subnets? Maybe, maybe not. You always want to plan for growth. Let's look at a different example. Let's say, okay, I've still got my 16 bits that I can play with within the firm. But let's say I want fewer subnets and have more hosts per subnet. Let's say I have 20 different divisions. 62 still gives me plenty of growth space. So 2 to the 6 minus 2, I've got 62 possible subnets with over 1,000 hosts I can have per subnet. Maybe that's better for your organization. This is just a mathematical example of how it works. So when we say that a network mask, a subnet mask, tells us which part of the IP address belongs to the network, we're counting bits. We're looking at the IP address in binary. That's the only way to understand how subnet masks work, is by understanding binary, because you're counting the number of ones in the subnet mask. So an IP address is 32 bits, a subnet mask is 32 bits. Just like a mask has to be the same size as your face. Anyway, you're counting the number of ones, consecutive ones on the left-hand side. That tells you the number of bits you're using for the network. There's a reason we don't do this in binary, because it's time-consuming and it's cumbersome to use. So typically, we'll use either decimal notation, so 255.255.255.0, or it's actually easier to use slash notation. Slash notation was something Cisco came up with years ago, and it was just a cool, hip way of showing a mask where you do an IP address and then a slash and then the number of bits in the subnet mask. So there are 12 bits here, so this would be literally called a /12 network. So just one example of how this works. A lot of private IP addresses will break at the decimal boundary. So for example, you'll have 8 ones, 8 ones, everything comes in 8s because we've got 4 octets of 8 bits. So 8 ones is in decimals 255. 8 ones is 255, 8 ones is 255, all zeros is 0. So a subnet mask of 255, 255, 255, 0 in decimal notation, we'd write that way. It's actually much faster to write this as a /24. 24 bits. 8 times 3 is 24. A /24 network.